work with we're still working with exponential functions, but we're going to work with, on our first page here, we're going to work with exponential growth and decay. So I want you first of all just to recognize and maybe circle right here, exponential growth model. The exponential growth model is y equals a times, in parentheses, 1 plus r, and then that is being taken to the t power. Now, if you note right above that, in that sentence above, it tells us what all those variables are representing. So y, the beginning of the equation, is representing the final amount, how much will you have after a certain given amount of time at a certain rate. A is the original amount, how much did it start at, whether it's money or number of people or whatever it is. The r is the rate of growth or decay, which is going to typically be given to you as a percent. They're going to say the student population at Valley City High School has been growing by about 2% every year. That's how they would give the rate, as a percent typically. Okay? And then you have to, though, before you can use it as an R in your equation, you have to change it to its decimal name. Such as, what is the decimal name for 2%? 0.02. So we have to divide it by 100, which is the shortcut of moving the decimal point 2 places to the left, and we have it in its decimal name. You can also work with it in a fraction name if you want. Typically, I'm going to guess you're not going to want to, though. Okay? And then t is representing time. Now, notice this is really no different than our exponential model, which is our exponential model, remember, goes like this. Y equals a times b to the x power. We still have a y, we still have an a. Our b is being replaced by what? 1 plus r. And our x is being replaced by t. So our t is really the x value. And so this is just a specialized exponential model. So when we have exponential growth, it's y equals a times 1 plus r to the t power. When we have exponential decay, now we're subtracting the r value from the 1. That's the only thing that changes. Which should make sense. If it's decaying, it's going down. So we're subtracting that rate. Why is it being added and subtracted from 1, do you think? What's the reason for that? Where'd that 1 come from? That would represent 100%. So in other words, we got to have the original represented, 100% of the original represented, plus how much did it grow by, or subtract how much did it decay by. So that 1 is 100% changed to its decimal name of 1. Okay, so from 100% changed to its decimal name is 1. Okay, there's a couple of examples up here for you to study on your own. I'll just leave that for you, and we'll just go right to work doing some practicing here. So, it says write an exponential growth function to model the situation. Here's where students can't wrap their heads around it. What you have to do is not even pay any attention to them. They want you to find something. First of all, they just want you to write a model that no matter what the amount of time was, you could use that model. So nothing should be in there for the only thing that should get replaced is the a value and the r value. That's the only thing that should be replaced when you're writing your model. So would you write that right here? Write an exponential growth function to model the situation. You're only going to replace the a and the r. That's the only thing you're going to replace, and then you will still have that y equals, you will have a value there for a. You'll still have in your parentheses 1 plus, but you're going to put something in for r, and then it's going to be taken to the t power. And the only thing you're going to do is add the r and the 1 together, just to clean it up a little bit. Then you're going to use it to find the value of the function after the given amount of time. Or in other words, you're going to substitute something in for t, and that'll help you get your y value. Okay? So number 1, annual sales at a company are $372,000 and increasing at a rate of 5% per year. And it says you're supposed to find the value after 8 years. Would you just ignore that right now? Don't even pay any attention to that 8 years right now. Right now, we just want to write what is our a value and what's our r value. What is our a value?
372,000.
Okay, so let's just write that down here in our notes so that we have. A is 372,000, what it starts at. R is 5%, which is 0.05, right? Okay, so now we're just gonna write our model that any amount of time, we don't even care about that 8 years right now. Given any amount of time, we could use this model to help us find out what their sales would be. Okay, so we're going to substitute into our y equals, let's just write the model first of all. We're going to substitute into that. And remember, we're only replacing the a and the r. So we're going to have y equals, we're going to put 372,000 in for our a value. We're going to substitute that 0.05 in for our r value. And we're still going to have t out there. And now the only thing we're going to do is clean that up a little bit. We can add the 1 and the 0.05, can't we? What does that become? Okay, so in other words, it's like our b value. Our b value becomes 1.05. There's our model that they were asking us for. So would you just make note of this is your model. This is really one of the answers. Because it asks us to do two things. Write a function, then find. So anybody have questions about setting that model up? Your model will always still have the y in it and the t in it. We'll still always have the y and the t in your model. Okay, now let's go write our model over here and let's use it. Y equals 372,000. And then we're going to have our 1.05 in parentheses. And what are we going to put in for t? 8. So now we're using our model to help find the sales. So y equals, remember what we did? We did 372,000 doesn't get multiplied times the 1.05, but instead the 1.05 gets multiplied, gets taken to the 8th power. Is that a crazy amount? You know what? I think let's try this. Let's start actually. I'm going to erase. Okay, you can do the same thing. Let's start doing it all in one fell swoop in our calculator. Okay? I think we're ready for that. Then we'll see if you're going to get the right calculation. So your calculator most likely should have the order of operations already programmed into it. So if you just type in 372,000 times 1.05 raised to the 8th power, and since this is money, we would round it to the nearest cent. So I'm not going to put up my answer until I see you actually doing the calculation. You just don't copy down mine, because I want you to make sure that you know how to use your calculator properly. $549,613.43. Could you make that happen on your calculators? And then we ask ourselves, does that make sense? Should it be bigger than our starting amount? Yeah. Okay. And it's for 8 years, 5%. Seems fairly reasonable. Okay. Now, the other thing I want you to do in your notes here is I want you to circle our model so that you realize that that is too one of the actual answers. We have two answers here. We have our model, and we have our dollar amount given the time of 8 years. So, exponential growth. How will we, when we look at an equation that has a b value, how will we determine if it is modeling exponential growth? how would we look at an exponential function, we pick out its b value, how would we say, you know what, this is exponential growth? Jacob? It's greater than 1. We added something to 1, so it would have to be greater than 1 to be an exponential growth function. So if I said to you that the b value for an exponential function was 1.2, what would the r value be? What would the rate have been? 20%, because 0.2, it's 1.2, so 0.2 got added to 1, and 0.2 changed to a percent is 20%. So that would mean there would have been a rate of 20% growth going on there, okay? Okay, let's go look at an exponential decay one now. So in exponential decay, remember we are subtracting from 1. So we have an internet chat room has 1,200 participants and is decreasing at a rate of 2% per year. After 5 years, we don't care about after 5 years right now. Remember? We're going to identify our A and our B. Okay, so let's go identify. What's our A for this one? 1,200, 1,200, and what's our R? 0.02. 0.02, so 0.02. Remember, our model for this one, for exponential decay, actually starts out as y equals a times 1 subtract the r to the t power. It's going down. So we're going to substitute in our a value and our r value. And we're going to keep our fingers off of our calculator because if we can't take 2 cents away from $1, we're in trouble. That's really what this is like. What is 1 take away 0.02? 0.98. Okay, thank you. Y equals 1,200 times 0.98 to the t power. That's our what? That's our model for this situation. So it's one of our answers. The only thing that got replaced was the A and the R. The Y and the T should still be in there. Then we will go and use our model to see what the number of participants would be after 5 years have gone by. So now we'll go over and substitute in 5 for T and calculate that. Now these are participants on the internet chat room, so what would we round to this time? Whole numbers, because these are people, right? So round it to the nearest participant. And again, we're working problems where we know what our y value is representing, so we give it a label. So you got rounded to 1,085 participants. Does our answer make sense? Why? Less than the original number. It was decreasing. So what do you think we could say about when we look at the b value? How would we decide if it's an exponential decay function? Be less than 1. Our b value is less than 1. Okay, so we got to be able to decipher when do we have exponential growth going on, when do we have exponential decay. What if I tell you the b value is 0.9? What's that mean? Decaying at a rate of 0.9 is my b value. Decaying at a rate of, that represents 90%, but where did that? So, Jacob? 10%. 1 take away the r value. So basically, 90 plus our 10 does give us our 1, so there's really a decay rate of 10%. So we have to figure out what added to our decimal gets us 1, and then that would be our decimal changed to a percent, so then it would be 10%. Okay, let's go on to the next side, where we have exponential growth and decay continued. And this is a very commonly used, in fact, if you have any money in a savings account somewhere, chances are it's getting compound interest. Compound interest meaning that, can anybody explain here what compound interest means? Or maybe your general business class that you took? There you go.
Isn't it like if you have money in a savings account, then you get a certain amount from the bank added to your savings?
Okay, so you get interest on the amount of money you put in there, your money's growing. But that's just, if we talk about it that way, we're talking about simple interest. They just keep adding some interest on the original amount that you put in. But if it's compound interest, here's what's happening. They're stopping at certain times of the year and they're saying, okay, we're gonna calculate the interest right now. So you're not only gonna get interest on the money that you put in the start, but you're gonna get interest on the interest that you've already earned too. So it's compounding it. So your money you put in originally plus the money they're giving you as interest is always earning more interest. So that's compound interest. And it has a fairly, intense formula right here. A equals P times, in parentheses, 1 plus, notice this time our R is being divided by N, and then instead of being taken to the T power, it is the NT power. Well, let's go and look at what all those things are telling us. This is really important that we understand what, there's so many variables in there, what are they all representing? A is the total balance, how much money is going to be in your account at that given time. P is how much did you start with, how much did you put in there in the beginning. R is the interest rate, and what do you suppose we're going to have to change it to? A decimal. N is the number of times the interest is compounded in 1 year. So if they say to you it's compounded annually, how many times would it be compounded? Annually. Once. Annually means just once. If they say to you it's been compounded quarterly, what would your N value be? 4, because there's 4 quarters in a year. 4 quarters in a year. Just like we have 4 quarters in our school year, right? Okay, quarterly is, your N value would be 4. What if they said it was compounded monthly? We'd use 12 for N. Okay, so we have to know what we use for our N value by being able to identify the words that go with it. And then T is the number of years. Okay, so there's another example there for you to study on your own. Let's go and practice it together here. We have, same thing. It says, write a compound interest function to model the situation. I'm going to tell you right now, again, the only thing you're going to replace are, again, you're going to replace this time the P value, which is our little A value. It's our starting amount. And you're going to replace the R value. And you're going to also this time replace the N value. So again, when you're all done, in reality, you should have left the Y value, which in this case is known as capital A, and the T value. That's it. Those are the only variables that should be left in your model, but they should be there. Okay, so, and then you're going to use it just like we did in the last one. So what's our A value in this one? Oh, it's not A. It's A, but it's called what this time? No, it's called actually capital P. So that stands for principal. How much did you start with? So what's that going to be? 17,000. Okay. What's our R value? 0.03. 0.03. Okay, and what's our N value? Compounded annually. 1. Annually means once. Once a year. Annually. If you have to have an annual physical, sports physical, how many times do you have to have it? Just once, yeah, every year. Okay. So let's go into our model now. First, let's write down our model. Capital A equals capital P times 1 plus R divided by N. That's going to be taken to the NT power. There's our model. And now we're going to substitute into that those 3 things we identified. So A equals, we're going to have 17,000 times 1 plus 0.03 divided by 1 times T. It's a good idea in these to make your T's cursive so they don't look like plus signs. And then we're going to clean this up. A equals 17,000. What's 0.03 divided by 1? 0.03. What's 1 plus 0.03? 1.03. Okay, so that's that one cleaned up. And what's 1 times t? It's 1t, so we could just actually call it t, couldn't we? 1 times something doesn't change it. Okay, there's our model. There's our model that they were asking us for. That would figure out how much money was in that account at any given time period. Okay, so now we're going to go and use it. So we're going to do A equals 17,000 times our 1.03 raised to the 6th power. Our t is 6. Okay, go ahead and calculate that. It's money, so we're going to round to the nearest cent. Again, not a good day to be without a calculator. And some of you are. Agree, disagree with me? Would you like to have a calculator? Agree? Does our answer make sense? Did our money grow? Okay, that's good. Okay. Anybody got questions about that before we do one more of them? And then we'll move on to our last page and more. So, again, the first thing we're always going to do is identify our capital P this time, our little r, and our n. It's always going to be our first move. So, go ahead and fill those out. See if you can figure out what you think they should be. Should capital P be little r, little n? So what should we have for our principal? 23,000. What should our little r be? 0.02. What should our n be? 4, compounded quarterly, 4 quarters in a year. Okay, and now we're ready to put it into our model, which I'm going to write down again because every time I write it down, I actually am going to remember it better. A equals P times 1 plus R over N to the NT power. A, I'm going to put my 23,000 in for P. I'm going to put in my 0.02 and then for R and my 4 for N. And then I'm going to put in 4 for n again, and take it times t. Okay? We can clean this up. We do the inside of the parentheses, right? That's 0.02 divided by 4. And it's a half a penny. So 0.005, and then add that 1. So we're going to have A equals 23,000. That's a sloppy. Try that again. 23,000 times 1.005. Can we clean up 4t? No, leave it 4t. There's our model for this situation. It can be used for any given number of years. And now we will use it. Okay, go ahead and use it. Figure out how much it's going to be after 8 years. How much money is going to be in this account, compounded quarterly at 2% for 8 years. We substitute 80 for 2. The next step, multiply that, we get 32 for our exponent. Put it in your calculator, run your cent. And ask ourselves, is my answer okay? There are none row. Good thing. Anybody get questions about compound interest function? Another type of exponential growth, just a type of exponential growth. A really common one. Okay, let's go to the last thing then, where we do some exponential decay, a specialized exponential decay one. Okay, a special type of exponential decay involves the half-life of substances. So we have this exponential decay formula that can be used for half-life. This is a half-life formula. What's our B value in this one? 0.5. Which 0.5 is really what fraction? 1/2. Half taken away from 1 is 1/2. So in reality, this was originally started as 1 take away 1/2. So it's 1/2, and it's always going to be that an exponential decay half-life. So they're just going to let you use the cleaned up one right away. So A again is the final amount. P is again the original amount. Here's the part that is the trickiest for students. T is not number of years this time. T is the number of half-lives in a given time period. So we have to figure out how many half-lives is something going to go through. So we are going to look at our example for this one. We have this substance called I'm not even sure how you say it. Anybody heard of it before? 212? Okay. Has a half-life of approximately 60 seconds. What does that mean? Has a half-life of approximately 60 seconds.
That's half of how long it's going to be around, I think.
Kind of, but we got to say it just a little bit differently. We have this substance, we have some amount of this substance, and after 60 seconds, what's going to be true? Only half of it's going to be left. Half of it has done what? Decayed. So if we started with, let's just start with an amount. If we started with 6 grams, how much is going to be left after 60 seconds? 3. After another 60 seconds, how much is going to be left? 1.5 grams of it. After another 60 seconds, how much is it? 3/4 of a gram. So in just 3 minutes time, in 3 half-lives, it's went from being a 6-gram sample down to a 3/4 of a gram sample. So that's what half-life means. So here they did, how much is left after a 25-gram sample after 300 seconds? So the T is not 300. The T is how many half-lives did it go through? So you take how much time they talked about, 300 seconds, and divide it by how many seconds are in a half-life, and we can see that it went through 5, would you put this here? It went through 5 half-lives. That's what happened. It went through 5 half-lives. That's what you have to find out. How many half-lives did it go through? It got 9 lives. Okay, how many half-lives is it going through? And then that's what you substitute into the formula for T. So we have our T, our 25, how much it started with. We have our 5 up there for T. And then we calculate it. Okay, so let's go try an example. Again, 2 things are going on here. Write a model, and then do after a given amount of time. Okay, so in our model, the only thing that's going to get replaced in our model is the p-value. Okay, so we need a p-value. What's our p-value for 30? So here's our model. A equals p times 0.5 to the t power. So the only thing we're going to do is put in A equals 30 times 0.5 to the t power. There's our model. So that would be our first answer. Now we need to figure out our T. We don't get to just go to the problem and say, okay, it's 6 years, or, oh, okay, it's after 3 years, or we have to go and say, what is our T gonna be? Our T is going to come from, we have to take the total amount of time that they're talking about. So has a half-life, this is important, has a half-life of 8 days, but we wanna figure out after 24 days. So what do we have to do? We gotta take 24 and divide it by 8 to see how many half-lives it went through in that amount of time. What would it go through? 3. So it would go through 3 half-lives. That's our T value. So now we go into our model. A equals 30 times 0.5 to the 3rd power. How many times it's going to be cut in half. And these we don't round unless the decimal just goes on forever. Usually they'll tell you what they want you to round it to. Typically these we just leave as the decimal we get. So what do we get for this one? 2.75? 3.75. Okay? And what are these measured in? Grams. Should our answer get smaller? Yeah, better. It better not be greater than 30 or it didn't do any decaying. It did some growing instead. Okay, you try the next one on your own now then. These are the trickiest ones. Well, yeah, maybe. Oftentimes this is the ones that students typically have the most trouble with. Again, every time you write that model down in its original state, that's when you'll start getting into memory. There's another thing that throws students off a lot. The number that's in the substances title. That number is only identifying a substance. Don't worry about using it. You don't use that number. Okay, that sodium 24. 24 is part of its name. It's not a number we're going to use. Okay, so I'm going to guess by now you all have your model. How are we going to get our T value this time?
560 by 15.
Okay, it's a 60-hour time period divided by the half-life of 15 hours. Okay, caution. Always make sure those match. Sometimes they'll do it like this. You might have a half-life of, like this one has a half-life of 15 hours. You might do it in days find out how much would be left after 3 days. Would you take 3 divided by 15 then? No. You have to change your days into hours, so be caution. Make sure that these labels match, okay? And then how many half-lives did it go through? 4, okay. And then we would substitute into our model. And this time, how much do we have left of our sodium 24? 2.5. How was this measured? In grams. Okay. This one has a pretty big half-life. Makes sense that it would be down pretty low, doesn't it? Okay, questions at all on any of the types of models that we used here? Those are the ones you'll be using in your homework. Okay? And then you have those other example problems at the top on those other 2 pages that we didn't go through. Maybe those will also be a reference point. Plus you have your lesson in the book that I always say now, so you need to make sure you're doing on your own.